Hello there, my name is Kevin Teran, and myself and Alejandro have created this video and the model we are about to present. So we chose to create a model to do sentiment analysis on the dataset we found called the Twitter Sentiment Analysis Training Corpus. The model will classify the input as either negative or positive. So let's begin. So for our imports, we imported JSON, which will become apparent later on. We import Gutierrez so that we have access to tools to work with our neural network and to make data machine friendly. And we also import Gutierrez preprocessing text as KPT and tokenizer, which are more tools to process the text and make it easier for the model to learn from the text. And then lastly, we import NumPy to work with arrays and load data. So before we continue, I'm going to talk about the dataset a little bit. The dataset contains roughly 1.5 million classified tweets. It has 4 columns: item ID, sentiment, sentiment source, and sentiment text. The 2 columns we will be focused on will be sentiment and sentiment text. The sentiment column has 0s and 1s, 0 for negative sentiment and 1 for positive sentiment. And the sentiment text column contains the actual tweet text. So here we define a variable training, and then we use NumPy gen from text, which is basically you're loading data from a text file, and in this case it's CSV. So we specify the file name, our delimiter, and we're going to skip the first row because the first row are the column headers, so we don't need that. And then we're only going to use 1 and 3, which corresponds with the second and fourth column, which are the sentiment and sentiment text columns. And as you can see here, after we printed it out for training, you have 0, which is the sentiment, and then the actual text for the tweet. Next, we will create our training data from the tweets. So here in train X, we put all the tweets in there, and then train Y, we're putting the sentiment values. For this max words 3000, we'll be using in our tokenizer here. So basically it means that we're going to be using the 3000 most popular words in our data set, and we'll create a tokenizer to help process our data. The tokenizer can be used to vectorize a text corpus just like the one we're using right now. Then we're going to use the fit_on_text method provided by the tokenizer to basically feed all the tweets to the tokenizer from the dataset, and it creates a dictionary that's similar to this comment, where the word will be the key, and then the number is kind of like your ID. And what this method does is basically creates a vocabulary index based on the word frequency. So lower integer means more frequent words. Next, we will use the tokenizer word index and set it to the dictionary variable. And this is why we imported JSON. We're going to use JSON to dump out to a file and save our dictionary, which we'll use in the next example. What this function does is it transforms each text, so in this case text here, in text to a sequence of integers. It replaces the text with the corresponding integer from the word index / dictionary. So now we're going to create an empty array, and then we're going to use this loop to populate it. What this loop does, it's going to take each tweet or input, and we're going to use the previously defined method to change each word to its ID in the tokenizer's word index, or in other words, the dictionary. And then we're going to append the new array of indices. And now we have a list of all tweets converted into index arrays, and then we're going to cast it as an array for future usage. So now we're going to create an empty array, and then we're going to use this loop to populate it. What this loop does, it's going to take each tweet or input, and we're going to use the previously defined method to change each word to its ID in the tokenizer's word index, or in other words, the dictionary. And then we're going to append the new array of indices. And now we have a list of all tweets converted into index arrays, and then we're going to cast it as an array for future usage. Then we create one-hot matrices out of the indexed tweets using sequence to matrix, this function here. And this method converts a list of sequences into a NumPy matrix. And the mode binary means that the words are present or not present. So 1 for present and 0 for not present. The reason we do this is because the variables are converted into a form that the machine learning algorithms can learn better from. And then next we take train Y and we set it to categorical, and we only have 2 categories. Now we import sequential, dense, dropout, and activation from QRS to create our model, and we're going to import time just out of curiosity because we want to know how long the model will take to train. So we declare model here, and that's going to be our actual model. We use sequential. It's a neural net that consists of a stack of layers executed in order. Then we're going to use 2 dense layers, 1, 2, and these are our standard neural net layers of inputs, weights, and outputs. We declared outputs of 512 because we felt that was a good number to work with. And we use ReLU activation because it's an activation function that we are familiar with. We've used it the whole semester. All activation functions are honestly viable here, but again, we chose ReLU because we're familiar with it. And the same applies to sigmoid here. And we also added 2 dropout layers, and the reason for that is we're trying to reduce overfitting. These dropout layers will randomly remove data to help with that end. Now we need to compile the model. So for our loss function, we chose categorical cross entropy. Our optimizer, we chose Atom. That's a very well-known optimizer. And the main metric we're concerned with is accuracy. We also did another model where instead of using Atom, we used SGD. So we're going to compare the 2 models just for a little bit. In the next line, we define time and then we print it. So we have our current time, which this was run April 2nd at roughly 10 o'clock or 10 p.m. Now we're going to fit our model with our training data. Our batch size is 32. We kept it low because it allows us to train our network quicker than if we used a large size. We used 5 epochs here because we tried more loops, but the increased time spent training led to overfitting, and thus it wasn't worth it. Our validation split here is 10%. So 10% of the input has been reserved as testing data. We did not want to use more than 10% because we wanted the model to have sufficient data to train on. And shuffle here means that the training data is shuffled before each epoch. And then again, we're going to check time and then print out the current time. So first, let's look at time. As I said before, it started at roughly 10 p.m. and you can see here it ended at 11:45. So that's an hour and 45 minutes to train this data set, which makes sense considering the amount of records in this set. And so now we can see here our loss, accuracy, validation loss, and validation accuracy. What we're most concerned with here is the validation accuracy. As you can see, after the first epoch, it's about 78.8%. And you'll see here that it slowly increases up to 79.35%. if you do one more epoch, it starts to overfit and the validation accuracy begins to drop. Now, heading back to the other example, our optimizer here is SGD, and we kept everything the same. So you'll see here, this was run, first starts at 3:30, roughly, and it ends at 4:30. So about an hour to train, which is significantly less time than the previous model. But you'll also notice here that our validation accuracy, at least after the first epoch, is significantly lower. But it jumps up a lot in the second epoch, and then continues to increase by a small amount. But it doesn't reach the level of validation accuracy that the Atom optimizer model does. So after the model has finished fitting, we're going to basically export our model to a JSON file so that we can load it in our next example. So that's what these next couple lines are doing. And we also have to save the weight in an H5 file, which an H5 file I had to look up. It's a binary data format that lets you store huge amounts of numerical data, just like all the weights that we have for this model, which makes sense since there's over 1 million records. There's a lot of weights to deal with. Now we're going to look at a small interactive example using our model. The inputs are similar to before. We're still going to use a tokenizer, but this time we don't need to fit it. We're going to use these labels, negative and positive. That's just so it's easier for us to read. And then we're going to load in our dictionary here using the JSON file that we saved in the previous example. Next we define this function here, which is going to check that all the words in our input are registered in the dictionary before trying to turn them into a matrix. And if it's not in there, we're going to get a message here, and the word is going to be ignored, basically. Next, we load in our model, and then we, initialize our model. Next, we load the weights. And then here is the interactive part. So now we can put in a sentence here, and then our model is going to evaluate that text and tell us whether it's a positive sentiment or negative sentiment. So I'm just going to type hello in here, and you can see that the model is predicting it's a positive sentiment with 83.6% confidence. And that's where these two weights are. The 16 being negative, 83 being positive. We can also put in another thing here to make sure that the negative sentiment is working. And you can see it's a negative sentiment here with 93% confidence. And that's all there is to our example. So from Alejandro and myself, thank you for watching our video.